Hey there. So in this lesson, we'll learn how to draw ray diagrams using laws of reflection. Well, our focus for this lesson will be plane mirrors. A plane mirror is represented by a straight line with a back side that has diagonal lines. So this front side of it represents the front of the mirror. The back side represents the silver coating at the back. This helps us figure out that what we're looking at on this side, which is the front of the mirror, is the real world. Anything at the back of it is the virtual world. It's like looking into the wall. There's nothing there except for the wall. But you still see, when you look into a mirror, you see a depth perception. Whatever, you know some laws of reflection already because you've been looking at mirrors all your life. So you know that when an object is closer to the mirror, at the back, it appears to be closer uh, as well. The farther it is, the farther it appears. So how is that image made possible in that mirror? We're going to learn that by following the laws of reflection. This is traditionally drawn on a piece of paper, but to address equity issues where people may not have access to a geometry box, such as this, where you have a protractor, you have a ruler, uh, I've created a virtual working space for you guys so you can do the exact same things by using technology instead. If for any reason you feel that you cannot work virtually and you have these tools, you can go ahead and do hand draw these as well if you like. At any point where you're asked to draw a ray diagram, you can hand draw it, take a picture, and upload it where it's required. I'm assuming that most of you would want to learn how to do this in using technology as well, because it adds an additional set of skills. So here we go. First of all, for any image to appear in a mirror, you need light falling on an object. This arrow here is our object. Imagine that's you standing in front of a mirror. So the only way you can see something in the mirror is if the light is on. If the lights are turned off, you look into a mirror, you wouldn't see anything, right? So light is essential. Why it is essential is because any light that falls on an object, imagine the tip of this arrow to be one part of that object and all light falling on that tip, it reflects in all possible directions. In 360 degrees, it's reflecting in all possible directions. The light that's of interest to us is the light that is falling onto the mirror. So the light that's falling on your face and then it's falling onto the mirror. How is that being reflected? That can help us figure out where your image would appear. So uh, to do this, we follow several laws of reflection or principles of reflection. As I demonstrate this to you, we'll learn those different principles. The very first thing you want to learn is that any incident ray, so any light that goes from the object to the mirror, is called incident ray. And let me draw that incident ray. In this program, if you want to draw a straight line, you want to look at this ruler on the side. As you see, there are three lines right now, so that shows me that this line is not absolutely horizontal. To make it absolutely horizontal, it needs to be just one line like that. So when I'm drawing it here, I'm looking at that ruler to make sure that it's absolutely horizontal. You want to be as accurate as possible. I'm also making that line slightly thicker, so it's 1 point. Instead, I'm making it 2 points. Okay, so that's an incident ray I've drawn. To show that that ray is going from the object to the mirror, I also need to draw an arrow here. So if it's on a piece of paper, you just draw a little arrow here. But because I don't have that privilege, I've kind of, I'll just use an arrow that I can draw right there. As long as it shows a an arrow symbol there, that's all I'm looking for. So that's an incident ray. Any incident ray that goes from the object to the mirror will be reflected at the exact same angle that it reached the mirror. In this case, because this ray is going absolutely parallel to this line here, this line we're calling it principal axis. Okay? This will come in more handy when we work with curved mirrors. So any line or any ray that is going parallel to that principal axis, you know, it's falling at 0 degrees uh, or 90 degrees. So if you're looking at the mirror as a reference point, then it's 90 degrees. Uh, if you're looking at the principal axis, then that's 0 degrees, right? It's the same parallel line. So that ray will be reflected right back. So first law is whatever angle the incident ray falls on the mirror, it gets reflected right back at the same exact angle. This straight line doesn't demonstrate that absolutely clearly, but let me draw that and then I'll show you another angled line. Again, to draw that arrow, I'm using the ruler on the sides to make sure that absolutely straight. That's somewhat accurate. So there's one ray of light that's going from the object to the mirror this way. If that's possible, then another ray is possible. I can either make another line, or because I've already selected all the properties of this line, what I can do is just do the select tool, select that line, copy it, Control C, paste, Control V, and then I can move that line around whichever way I like. So I want it to start at the arrow, and then it could go at any angle. As you know, light that falls or that comes from that object, it could be going at any angle possible and hitting this mirror. So why not this random angle, right? And why not this random angle where this light hits directly at that principal axis? I'll also take that arrow with it, so it helps me figure out or helps me show that that is an incident ray that's going from the object to the mirror. Okay. Now this is where our use of protractor and angles comes necessary. This is an incident ray. It is reflected at the exact same angle. And what that means is it's reflected at the exact same angle that it makes with that principal axis. Okay. So here's a protractor. I've used a 360 protractor to make things easier for you. And usually you would have a D-shaped protractor. This one makes things easier in this program because you don't have to move things around too much. So what I'm doing right now, if I want to zoom in and show you, is I'm putting that protractor exactly where the incident ray meets the mirror. That's what you want to do. I'm using some lines as a reference point. Principal axis, for example, is along this 90-degree line, and mirror has to match as accurately as possible your 90-degree line vertically. So I feel that's as close as I can get. I've placed my protractor there. This can help me measure angles now. You see, the angle that my incident ray makes with the principal axis, so this angle right there, it's starting at 90 here. You can think of it as 90 to 80, or you can think of it as 10 degrees. 90 to 80 is 10 degrees, and then 11, 12, and 13. So it's roughly 13 and a half degree angle. Therefore, the reflected ray must be the same exact angle. With this protractor, all I have to do is go down here at the exact same point. So 1, 2, and 3, 3.5 steps away from 80, 3.5 steps away from 80, or you can think of it as 13.5 degrees. Once I found that, I want to draw my incident ray there. How am I going to draw that? I'm going to either draw a new line or copy and paste an existing line. I'll make it start at that point, and then I'll make it go at an angle that I know. So I'm dragging this line until I reach 13 and a half. This is 10, 11, 12, 13 and a half. Okay, so that's as accurately as I can seemingly draw it. That's my reflected ray. Okay. I don't need the protractor right now for the next couple of steps, so I'm going to zoom out and put the protractor away in the geometry box, okay, away from my side. So this is the reflected ray. Again, I want to make sure I show what that reflected ray is, in which direction it is going in. So I'm going to draw an arrow to represent the direction in which it is going. Okay, so technically this is all we need. Here's the second principle of reflection. When you extend, or wherever the reflected rays meet, so in this case we have one reflected ray right there that's going into the mirror and then coming right back, and another reflected ray is this one. So the law of reflection is that wherever the reflected rays meet, that is where your image will be formed. In this case, this reflected ray, as you can see, if it keeps going and going and going, it's going there. This one is going down here. So are they ever going to meet in this real world? The answer is no. They are never going to meet in this real world because they're going farther apart. That doesn't mean that they're not going to meet. They're actually going to meet in the virtual world. You must extend those reflected rays in the virtual world, and you can kind of see where they might meet, right? To help you with that, you can again use this protractor if you wanted to. In real world, what you would do is you'd use a ruler. Let me show you using a ruler first, and then I'll show you the easier way using the protractor. So I'll drag a ruler here. I'll make it turn at an angle that's similar to that line, and this can help me here because now I know that an angle that I drew was 13.5 degrees. So what I can do with this angle is make it 340. You can do your calculations. Is 347 close to that? You know it's going to be the same angle. So that's a cool thing about this program, that it shows you an angle there. If you don't understand that, you don't want to worry about that. Just turn it until it's parallel to that line. That's all we're looking for. So why we're looking for that is so that we can draw a line parallel to that on the back side of that mirror. So once my ruler is parallel enough, what I'll do is either copy or draw a new line. Now for this line, there needs to be something special because it's at the back of the mirror. It's in the virtual world. Any line you draw in the virtual world needs to be dotted line. So I'll go to this button there, make it a dotted line. That represents that it's behind the mirror. Okay, this seems straight enough, it's parallel enough. So that's the reflected ray extended into the mirror. Same will happen to this reflected ray. It will also be extended into the mirror. So I'm going to copy that dotted line, and I'll put this ruler away for now because I don't need a ruler to draw a straight line. Or do I? Well, let's see. We have a ruler right here in this program, so we don't need that picture of a ruler. Here's how I'll do it. I'll take that line, I'll drag it right there, and then to make it straight, I'm going to hold it there, and I'll observe that this ruler right here. You see this ruler in the program? So I'll just make it straight as I can make it. Okay, so this is where the two reflected rays are meeting. That is where my object's image will be formed. So I can copy an arrow like that, or to accurately represent it, I can create an arrow If I give you any object other than an arrow, I'll make sure that you can copy that image. It's the same. Yes. So here we have it. This is the arrow. That is the image that we're looking for. Okay. Now, these are two reflected rays. To be absolutely sure that you have the right point, what you want to do is draw a third reflected ray. So why we do that is because if you have two lines, they could meet at any random point, right? These two lines could have met here, or if this line was at a slightly different angle, they could have met here, 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 anywhere, right? So if I made a mistake in measuring these angles, then this may be an incorrect answer. So to check my answer, what I can do is draw a third ray at any other random angle. So I'm copying that incident ray, originating it again from that object, and drawing it at any other random angle. Okay, why not this angle up here? Now, how will it be reflected? What reference point do I use? So if you're not working with the principal axis and you need another reference point, what you can do is draw a normal line. Okay, you can draw a dotted line that goes right through that point where the incident ray is hitting the mirror, and that line is called the normal line. It's, you can think of it as a copy of this principal axis, just so that we can use an angle measurement. Okay, so this incident ray, which needs an arrow of its own as well, once you get used to this copying and pasting, it's quite quick, straightforward. So this is the incident ray. I know it will be reflected up there somewhere, but exactly at which angle, I need a protractor. I may want to zoom in, be more accurate. So again, vertical line, this blue line meeting the plane mirror, and then horizontal line meeting the 90-degree angle. So the angle at which this is falling to the normal is, if you see, from 90 to 80, and then to 75, and then 74 there. These numbers, if they confuse you, all you have to do is start from here at 0. Okay, just count forward: 5, 10, 15, and then 16. So it's a 16-degree angle that this is making. I want a 16-degree angle up here. 5, 10, 15, 16, right there. That's the point. So copy and paste a line that originates at that point and then reaches 5, 10, 15, and 16 degrees. Okay, that's my reflected ray. Now, here's a quick part. I know that this is not the line I'm interested in. I'm interested in the line that will be extended back into the mirror. So instead of using another ruler, what you can do with this protractor, which is a 360-degree protractor, is draw a dotted line right there. You know that if this line is extending back into the mirror, just like here from 90 you went to 74, you're doing the same thing. You're going from 90 to 74. So I'll just take a dotted line, place it there, and then extend it. This is 80, 75, and 74. That's 11 degrees. Sorry, 16 degrees, right? So that's my line. If I extend it so that I reach the arrow or beyond the arrow. Now, when you extend it, be careful that you're not looking at the arrow, but your angle. You're still looking at this 80 degrees, and then 75, and then 74. Okay, that's my reflected ray. Zoom out, put the protractor away. You see where these three lines meet? Now, if two lines met at a point, that could be any random point. But if three lines meet at a point, if I zoom in there, you can see that it's not exactly accurate, but it's quite close enough. So that's what you're looking for. Because of all these little nuances on paper or using technology, you will never get it exactly right. But as long as it's reasonable enough, three rays meeting there, I know for sure that my answer is right. Okay, that this is where these rays are meeting, and that's where my object's image will be. This is a ray diagram for just one point. We've drawn three incident rays and three reflected rays. We've extended them into the mirror. Where those three rays meet, we put our object's image. The laws that we followed to make this possible are: first, any incident ray that falls on the mirror, at whatever angle it falls, it has to reflect back. So the reflected ray has to be the exact same angle as the incident ray. The angle it makes with the principal axis or with the normal, this line is the normal, we call the angle that incident ray makes angle of incidence, and the reflected ray's angle is called the angle of reflection. Okay, so this angle here, this angle is angle of incidence, this angle is angle of reflection. Same here, angle of incidence, angle of reflection. Then the second law we followed is wherever the reflected rays meet, our image is formed. Those reflected rays may not meet in the real world, they may meet in the virtual world. Wherever they meet, we have our image formed. Now it's time for you to practice.